Hello everyone. In this short video, we will be seeing how to do a statically determinate beam analysis and how to correlate the software finite element analysis results with the hand calculations. So this is a very simple example of a simply supported beam with an overhang. You have a point load on the member AB and another point load on the point D, and then you have a uniformly distributed load over the members BC and CD. The total length of the beam is 6 meters with three 2-meter intervals. And the purpose of this analysis is to calculate the reactions at point A and point C. So basically we have two types of supports here. Point A has pinned support and point C has a roller support. So let's see how to do such an analysis using a finite element software, Midas Civil. So here I have opened the blank Midas Civil window. You can go to File and press New Project to open up a new project file. So as soon as you do that, you will find that your menus get active. You have a ribbon menu system here, starting from structure type, node element, which is basically your modeling tools similar to your AutoCAD, and properties. You can assign materials and sections which are essential to run the finite element analysis, and then boundaries where we define the pinned or roller supports or any kind of support conditions. Then we apply the loads using the load menu, and then we perform analysis. Then we see the results, which include reactions in our case, and we can view the results on this main model window. We can view the results graphically, as well as we can extract the results in the table format. Now just to give you a brief introduction to the graphical user interface, we have the dynamic view on the right side of your screen, which is self-explanatory, because you can just click on the side view and on the isometric view, top view, to change or browse through different views in your model. And then you have the works tree on the left side. So whatever you do in your model will be enlisted out here, so you can have a check of what features you have used in your model, and whether you have done it correctly or not. You can also edit it directly from the works tree. So let's start the modeling process. So this particular analysis we will be doing in a 2D mode. So basically the finite element software supports the 3-dimensional as well as 2-dimensional analysis. So for simplicity, we have chosen a statically determinate structure, a beam. So let's go for a 2-dimension analysis. So to set the mode into a 2-dimension analysis mode, we go to structures, structure type, and change it to XZ plane. So XZ plane, just to explain you what XZ means here, is this you see is the top view. So X and Y are the default horizontal axis, and Z is always vertically pointing upwards. So it follows the right hand rule with Z pointing upwards. So that's the XZ plane, and click OK. So only the vertical and horizontal forces or deformations will be taken into account. Let's go back to the PDF file. Okay, so we need to create a beam which is 6 meters. So first of all, we need to be careful about the units that we are using in the finite element software. So we need to use meters and kilonewtons in this example. So we can change the units to kilonewtons or any other units from the status bar here at the bottom of your screen. Or we can go to Tools, Unit System, and make sure it's kilonewton and meter, and click OK. So I'll go to Structure and go to Base Structure and select Beam here and enter the distance. So that's 3 at 2.0. So three beams, three elements at 2 meter intervals. That will make a beam of 6 meters. Add. And for the material and section, I can keep it default as 1 and 1. So basically in 500 element software, the materials and sections for a given element or a given beam is denoted by number internally. So by default we can set it as 1 and we can define it later on, what is the material and what is the section. So we click OK and we have got a beam here now with 3 divisions. Now we define the materials and section for this beam. So I go to properties, material properties, and click on add. So we can select any material from here, say it's steel. We can select the standard and select what type of material we want, or we can go for just user defined material and simply define the modulus of elasticity. So let us say it's 2 into 10 to the power 8 kilonewton per meter square, and we give a name to it, say material 1, and click OK. Similarly, we do the same for section. We go to properties, section properties, and we say add, and we define a section, this time a rectangular section, and just name it section. Select user type and select the dimensions as 0.5 meters and 0.5 meters. To see the properties for this section, you can always click on show calculation results. So it will show you the area, moment of inertia, and centroid location of this particular section. So I'll click OK and the section is saved, and as soon as you click OK, you will see the shape of the section appears on the screen. So this is the 500 millimeters by 500 millimeters section. Let's see from the isometric point of view. So click here, and that's the isometric view, and you can see the full beam model with the shape included. So let's see what kind of boundary conditions we are looking at. So we're looking at a pin condition here at point A and a roller condition over here at point C. Let's see how to apply these. Okay, so first of all, how to know if which is point A and which is point C in the software just by looking at the model. So for that we have a node numbering system. Every finite element software has got a numbering system, so by which it identifies the structure internally. So what we do is we turn on the node number. So we click on this option, display node numbers, and you will see the numbers appear on the screen as 1, 2, 3, and 4. They are in the order of their creation. So the one which was created first will be named as 1, and so on. So I've changed it to the top view again. Now let's assign some supports. So a point A is node number 1 and point C is node number 3. So we go to boundaries, define supports, and first of all we define a pin support. So what is a pin support? A pin support is a support that will restrain vertical and horizontal translation but will allow rotation. So here we need to restrain the translation directions for X and Z, X being the horizontal, and Z being the vertical. Now to be more clear, let's display the viewpoint, which will clearly define which is vertical and which is horizontal. So I'll go to display, this particular option here, and select view and select viewpoint and click OK. So here at the right corner of your screen it will appear Z is the vertical right now and X is the horizontal. So I'll restrain dx and dz, which are the translation or displacement degrees of freedom, and will keep everything unticked, like rotation should be allowed, so we don't restrain the rotation. So rx, ry, rz are all unticked. Now we select this particular node. So how to select? We have an array of selection tools at the top. So we just select single and just click on this node. So node 1 is selected. How do you know that it is selected? Because it will be highlighted here, and as well as the number will be displayed on this box, the node selection box. So click apply. So the supports are now applied. We do the same for point 3. We select by clicking on node number 3, and instead of dx dz, we only choose dz this time because it's a roller support, which means it allows horizontal translation but restrains vertical motion. So we just untick dx, so we are allowing dx direction motion, and we're restraining dz, and click apply. So the supports are applied like this. I'll close this now, and you can see in the works tree the information has been entered, whatever you have entered in the model. If you want to edit anything, you can always say right click on a particular entity and go to properties and edit that entity. So now we move on to the load conditions. So I'll just quickly save this model. Okay, so we now move on to the load conditions. That's the loads. Now for applying the loads in a finite element model, we first need to create load cases. So we create the load cases by, say, giving it a name, and say for example a load P, a point load P, and say a uniformly distributed load small w. So these names will be used to see the results for a particular load. Also will be used by the software to identify which analysis case it is. So we will name the load cases. So we have two types of loads in this structure: point loads and uniformly distributed loads. You can include them under the same name, or you can separate them out to see the results separately. So in this case we'll separate them out. So we'll go to loads, static load cases, and we'll type in name as P and type as, say, user defined add. Then we'll change the name to small w, for instance, add again. So we have added two names, and we'll close this. Now let's see where the loads are applied. So the loads are applied at point B and point D, the 15 kilonewton loads. So let's start by applying those loads first. Okay, so our point B is node number 2 and point D is node number 4. So let's go to loads, and for the point loads we use the option of nodal loads. So select nodal loads here, select the point load case name P, and in the FZ we enter -15. Why FZ? Because we are applying the force vertically, and why minus? Because it's in the vertically downward direction. So it's by default the Z axis is pointing upwards, so we need to enter -15. So again, just like supports, we select these nodes where we want to apply the load. So select node number 2 and select node number 4. So you have selected 2 and 4. You can check it from the node selection box. Two nodes are selected, and you click apply. So you can see two arrows here. They denote the application of the load pointing downwards, so that's correct. So I'll now close this. Next is the UDL, the uniformly distributed load. So for the UDL, you will see that it's applied on the member CD and applied on half of the member BC. So to create this half, we need to divide this element or the member BC. So let's see how to do that in the software. So we have to divide this particular member so that we get a midpoint here, and we can apply the loads from that midpoint to the end of this beam. So we go to node element again, and this time we select divide elements, divide, and again use the select single feature, and just click on this element, the middle element. You can also display the element numbers. So if I click on display element numbers, you'll find this element is named as 2. So I can click on this member, so it's highlighted and it says 2, which means it is selected, and you can enter the number of divisions you want to divide this element into. So we want 2 divisions, and click apply. So we've got a midpoint now. You can see the element has been divided. You have a new element number 2 and 4, and I'll close this. Okay, now let's apply some load on top of these elements 4 and 3. So let's go to load, and this time we select element load. So element beam load, select load case name as W. Of course we can keep the load case name same, but then in that case both the loads will be combined directly. We can keep it separate if we want to see the results separately for the UDL and for the concentrated loads. So again, here we select the load type as uniform loads, uniformly distributed loads. Direction is global Z, vertical direction, and the value of W is -2, minus because it's in the downward direction, kilonewton meters. And let's select the two elements here, this one and this one, which represents the length over which the load will be applied, and click apply. So I'll change the view to a line view so it's more clear. So you'll click on this option here, the hidden option. So I have a line view now, and I will switch off all the node numbers so it's better viewing the model. So here you are with the load conditions applied. And I'll close this dialog box, and now we will analyze this model. So we'll click on the perform analysis button here, or we can go to analysis and perform analysis from here. So as soon as you click on perform analysis, a window pops up which shows the status of the analysis. The message window is very important because if you have done any errors in the model, like if you forgot to assign a support condition, so those kind of situation, the message window will display the instability warnings, and you can always go back to the model, refer to the node numbers or the element number which are displayed in the message window, and check or correct your model based on that. So the analysis is now complete. Now we go to results, and we start looking at the reactions. We go to reactions here and select the load case name. So say the load case P, which is the point loads. Select values here, and if there is a small box over here, if you click on that, you can change the number of decimal points, say 2, and click OK. So you have got 30 kilonewton as the load, as the reaction due to the point loads. And let's select W, which is the uniformly distributed load. So due to the uniformly distributed load, you have these reactions. Now if you were to combine the two results and see what is the total reaction due to both the load cases, for that we have a feature called the load combinations. So you can go to results, load combinations, and just quickly generate a combination, say name it as combination, and the type is add, so you're basically adding the two cases. So you select P and factor 1, W and factor 1, and click close. And now we can select the combination and click apply to see the results. So there you go, you have the vertical reactions added up from both the load cases, and this is the total reaction that you're getting. Since we don't have any horizontal force applied, so we don't have any horizontal reaction at the pin support, so we have only vertical reactions. Now if you were to see the results also in the tabular format, we have a result table option. Go to result tables, reaction, select the load case combination, and click OK. It will give you the reactions at node number 1, which is your point A basically. bend support. You have a vertically downward reaction, and on node number 3 you have reactions vertically upwards. And here this particular table shows you the summation of the reaction, which is very critical in checking whether the model is correct or not. You can see the summation of the reaction is 36, which you can actually check with respect to the total weights applied on the structure. So you can add up the total weight, total loads applied on the structure, and if they're coming equal to the summation of reaction, that means your model is transferring the forces correctly. So that's basically it for the finite element analysis model. Let's see what the hand calculations suggest. So I'll go to the end of this document. All these documents will be available in the description of the video on YouTube. So this is the beam example that we took, and you have the three unknowns here, and you have three equations for solving it. So that's a statically determinate structure. So horizontal reactions will be 0 because we don't have any horizontal force, so that HA is automatically 0. To determine VC and VA, we can take moments first about A and then about C and add them up to 0 to find out the unknowns VA and VC. And to check the values, we can add up VA plus VC and see if it's equal to the applied loads or not. So after the hand calculations, we obtain the theoretical results, which are exactly same as the finite elements of a Midas civil. So hence we can conclude that the modeling process is correct and the representation of the loads and boundaries has been correctly applied on the structure, and that's how we can model a simple beam example in Midas civil. To know about more examples, stay tuned to Midas UK YouTube page for more tutorials on Midas Civil and Midas other Midas packages. That's it for now. Thank you very much.